In this video, we're going to look at the Diels-Alder cycloaddition, and this is a very important reaction because you're going to be forming two new carbon-carbon bonds, and it's also going to introduce you to a new type of mechanism. So let's just look at a quick overview. So you're going to need two very particular types of reactants for a Diels-Alder reaction. You're going to need a diene, where dienes are going to be the molecules that have your two double bonds. And you're also going to need what we call a dienophile. So it's going to be a single double bond alkene of some kind, but it's also going to need some kind of electron withdrawing group attached to it. And we'll talk about some specific examples a little later. But again, you're going to need a diene and what we call a dienophile. So dienophile just means diene, loving or wanting, okay? And what's going to happen is you're going to form two new carbon-carbon bonds. So you're basically going to connect the two pieces together. You do form a ring. And then the other thing that's going to happen is you're going to go from a diene to just a single double bond. So these electrons are going to kick in. These are going to kick out to form a new bond. These pi electrons will come form this new bond. So what we get, I'm going to try to color code this so we're not losing track. And numbering is sometimes a good thing with these. So the double bond has shifted here. I have now formed new bonds between those carbons. And in this case, I'm ending up with a cyclohexene. So again, two new carbon-carbon bonds. Now notice if you look at the mechanism I drew, it's in a cycle. So electrons are moving in a circle. This is called a pericyclic reaction mechanism. And that really is referring to the electrons moving in a cyclical fashion. Everything happens in one step. So where the Diels-Alder reaction can get a little more interesting is if we need to think about what makes a good dienophile and a good diene. So good dienophiles, like I said, you have to have a double bond or a triple bond. And that bond needs to have something that's electron withdrawing. So one example is a carbonyl, and it could be ketone, ester, aldehyde. Any of them is going to work as long as that carbonyl carbon is what's attached to your double bond. And the reason we need this is we can draw a resonance structure. That is going to put a positive charge out on where was the double bond. This helps that flow of electrons. The dienophile is going to act as the electrophile. So now that I have the positive charge out here, it's more electrophilic. So a ketone is a good example. Another example is, like I said, would be an aldehyde. We could also have an ester, and that could be any R group out there. You can also have cyclic dienophiles. And one common example looks kind of funny, but kind of like a double ester anhydride here, kind of like double electron withdrawing. You can also put that into a six-membered type ring. Here, notice there's two double bonds, so you could actually do two Diels-Alder reactions, one on both sides. Cyano groups are also good electron withdrawing groups. Triple bond, you can have any of the same options as well to make a good dienophile. So there are a lot of options. And to know if something's electron withdrawing, see if you can draw a resonance structure that will pull the electrons in this double or triple bond out, and then you've got a good dienophile. If we want to think about the dienes, the key piece for the diene is that you do have a conjugated diene. So this is going to be your simplest fashion or example. And notice I've been drawing it in this direction where both double bonds are pointing in the same way rather than like this. So the first one I drew is what we call S-cis. And the S means we're looking at cis around a single bond. So cis trans, we don't usually refer in single bonds as cis or trans because they can freely rotate. And things do freely rotate here. All right. So both of these cis, S-cis versus S-trans are possible. But for this reaction to occur, it has to be in this S-cis conformation. So as long as it can get there relatively easy, it will work. So let's look at another example. So we're going to have a diene. Let's look at, oh, change that for a second here. Let's look at this diene. So notice that it is S-trans. We're trans around this single bond. If I want to make it S-cis, right, so I've rotated here. Notice the double bonds were actually cis. So the carbon groups are on the same side. So that means they're pointing in here. We've got some major steric interaction. And this particular diene is not going to undergo Diels-Alder because it can't easily rotate into the S-cis conformation. One diene that is very commonly used and works really well is going to be cyclopentadiene. And the reason for this is it has to be S-cis. There's no way that it can ever be S-trans. Even though it's a single bond here, being in a ring, it's locked in that S-cis conformation. So cyclopentadiene is a very common diene that's used. Sometimes you'll also have the ether version where you have oxygen in there. That also works. Something else that will affect your your diene reactivity is if you have substituent groups on the diene. If you have a group either here or here, you want that to be an electron withdrawing group. If you have it on the ends, you would want those groups to be electron donating. And much like with the dienophile, we had to have electron withdrawing so that resonance pulled the electron density out and gave us a better electrophile. Here, you could do the same thing. If it's in that X position, electron withdrawing will put your electrons in the right spot for the pericyclic reaction. If it's out on those Y positions, again, resonance would put the electrons in a good spot for the pericyclic reaction. So one thing that's nice about our Diels-Alder reactions is they are what we call stereospecific. So most of the time you're going to get a single product, a single stereoisomer. So your cis-trans stereochemistry of your dienophile is going to remain in the product. So for example, if I had this dienophile, notice that the double bond is cis. So they're going to stay in that orientation in the Diels-Alder. So if I react that with just a simple diene here, we'll see that the product formed, you're going to keep that cis conformation. So the ketone and the methyl group are going to be on the same side of the double bond. If your dienophile was trans, those groups are going to remain trans in the product. So they will be on opposite sides of the ring. So that's one way that we have the stereospecificity. Another thing is we're going to have what we call a difference between endo and exo products. So whenever we have a bicyclic product, which we will get when we start with a cyclic reactant, you're going to always form the endo product. So let's look at an example. So if I start off with the cyclobutadiene as my diene, and then I will have my dienophile. What's going to happen is, again, we're always forming the double bond between the end of the diene carbons and the two carbons of the dienophile. So that means this carbon that's here at this point, we're going to kind of think of it shifting upwards. So these are sometimes hard and difficult to visualize. So finding 3D representations, and there's a lot of them out there online to help you visualize this, I strongly encourage you to do that. But numbering can also help. So if I number those 4 carbons, I'm going to have 1, 2, 3, 4. So I got 1, 2, 3, and 4. I know my electrons are going to shift around, so my double bond is going to be between 2 and 3. Carbons 1 and 4 are the ones that are attached out here to this, I'm going to call number 5. And I want to kind of draw the number 5 up so it's out of the way. 1 is going to be attached to A, and 4 is going to be attached to B. So I'm going to make a new bond. Here's A, and a new bond, here's B, and those are attached to each other. And then A has the ketone group on it. Okay, so that's how you get things linked together. This endo versus exo idea, if I focus in on carbon A here, that carbon also has a hydrogen on it. So that hydrogen could either be up along with the point of my bicyclic structure, or it could be down, which then in turn puts the ketone either up or down. So this is considered exo, and the location that I have this green spot is endo. So your carbon group is always going to be endo. And the reason for that is it's better to have the hydrogen exo so that it's what's interacting with that carbon rather than this bigger bulky carbon group. So I'm going to get rid of this H because I know the carbon group needs to be endo. And I also know that then that makes the hydrogen exo. So if you're having trouble drawing this, it helps to draw the hydrogen in so that even if I can't quite tell the angle, if I see that the hydrogen is up above the carbon group, I know that you're doing exo versus endo a little more clearly. Okay. So let's look at one more quick example where we have this bicyclic product and we need to draw endo versus exo. So this time let's react with this diene, and then the dienophile, let's use an aldehyde this time. So again, if you need to number, I encourage you to do so. So here's my 4 carbons of the diene that I care about. I'm going to make a new bond between carbon 1 and what I'm going to call carbon A of the diene, the dienophile. I'm also going to make a new bond between 4 and carbon B. My double bonds are going to shift around. So in my product between 2 and 3 is the new double bond. Here's carbon 1, here's carbon 4. Then I have the oxygen that's attached to both 1 and 4. So there's that oxygen. Then 1 is attached to A, 4 is attached to B. Those two are linked together. A then has the aldehyde, and that aldehyde needs to be endo. So I'm going to draw it down, and then my hydrogen is going to be exo and up with that oxygen. So it's kind of awkward. Even I didn't do a great job drawing that. So there I kind of just did it. If I'm not talking at the same time I'm doing it. So I'm going to do it one more time. So watch kind of the pattern that I use to draw these structures. So there's kind of a standard version of what a bicyclic structure might look like. And again, this is what's going to work if you've got a 5-membered ring to start. If you have a 6-membered ring to start, because you can have a 6-membered diene. So here my new bond is again from the ends of the diene to the dienophile. But now between my carbons 1 and 4, I actually have 2 carbons. So again, I'm going to draw my 2, 3 new double bonds. There's 1, there's 4. Now if I go up, I'm going to have 5 and 6. 6 is attached to 1. So here's 1, 2, 3, 4, 5, 6. So my 6-membered ring. 1 is attached to the dienophile, 4 is attached to the dienophile. My group is going to be endo, so there would be the products.